So this is the noise texture. I'll give you a more simple explanation at the start and then move on to a detailed explanation. So this dimension thing just depends on the situation. For example, here I'm using a plane, so I should really just use 2D because it's a 2D surface. If you're using UV maps, you should also use 2D. If you're not using UV maps and you have a 3D object, then you might want to use 3D because otherwise it will look really distorted. The scale, you can use this to make it bigger or smaller. And then the detail to increase, well, the detail. So if you're using this to create mountain ranges, this will make it seem like there are smaller variations in the surface, creating something like rocks. Then the roughness increases the importance of like the smaller details. So if I increase this, then these larger black areas or white areas will all blend together, and then won't be able to distinguish between my tertiary and secondary and primary details anymore. And if I decrease this, you'll only get like the primary details. Then the distortion really just does what it says. It distorts the space, so the input vector, which is pretty much the same as adding a noise texture to the input vector. In a previous video, we already made this value noise, and a better version of this value noise, because this is really too blocky in most cases, is to use Perlin noise, where instead of just putting a random value at each corner, we're putting a random gradient at each corner and using that to determine the noise value. So even just using the Perlin noise on its own doesn't look that great. So what we can do is to do something like this here, where we make multiple copies of this Perlin noise and add them together. So as you can see, this is one copy, and then if you look at the second copy, I've doubled the scale. In the third copy, I've doubled the scale again, and then again and again. So these ones create finer detail than this one. This is for more primary detail. So we can add these two together, just like this. Now if I set this roughness value to 1, then we're just really adding these together. But if I set this to 0.5, then we're multiplying this one by 0.5, so decreasing the importance of the second noise texture, and only then adding it to the first one. And then for the third one, we're multiplying by 0.5 by 0.5, getting 0.25, so making it even less important, and so on for all these ones. And really, sometimes this is referred to as using octaves, because we're doubling the frequency or the noise scale, but we're halving the amplitude or the roughness by the roughness. Because the roughness is 0.5, we're halving the amplitude. But obviously it doesn't need to be 0.5. You can change this. And this roughness value is the same one as this one here. And the detail, this one is the one that determines how many copies of these we have. So if you look at the final result, you can see that this looks very similar to the result you would get off of the noise texture if we set this to something like 0.5. So if we look at the code for the noise, fractal noise, because really this is called fractal noise, then you can see that there's this loop here, which goes n times. And what is this n? This is just the int of the octaves, so just the integer part, because we can't loop 0.5 times. And this final 0.3 value, that's this remainder here, this is multiplied by the final one. So for example, if you set the detail to 0.2, then we'll get the basic noise texture and then one copy of it added, multiplied by 0.5 like normal, and then still multiplied by 0.2, because this is not completely 1. So in this case we would multiply it by 1, while in this case we multiply it by 0.1. And each iteration, what we do is we get the noise texture, simplex noise, then we add to the previous ones we've already added this noise multiplied by the amplitude. Then we keep track of how many times we've added an amplitude so that we can rescale everything from 0 to 1 to get it to between 0 and 1. And then we make the amplitude smaller by multiplying it by the roughness. So now, and finally we double the scale. So if you look at this noise texture, increasing the detail just adds more and more noise textures, but this means it's going to be a lot slower, because every time this increases by a whole number, you're adding another noise texture. So you should try to keep this detail as low as possible. If you set the roughness to 1, then you won't be able to make a distinction between the different noise textures that you've added together, but in some cases you might want that. If you keep the roughness low, then the value here will go down very fast because it's exponential, and you won't be able to notice the higher detail levels. So if you have a low roughness, don't bother setting the detail high because you won't be able to notice it anyway. Now this distortion value is not included here, and that's included in this part. And really what this says is the distortion is not 0, because if it's 0 we shouldn't do anything. Just add to the input vector some random offset along the x and the y, or x, y and z, depending on whether we've set the dimension to 2D, 3D or 4D. So for example here we're creating some random noise and using that as the distortion. Now we're multiplying by the distortion, so if you have a low distortion, then the offset won't add as much as when you have a distortion of something like 10, then this offset will be 10 times as large as when you have an offset of 1. And the output, the value is just the value that we got from computing this one here. And the color, the red channel is the same. So the red channel of this one, so that is separate RGB. The red channel will be the same as the factor output. Then the green and blue are different noise textures as well. So as you can see, these are also computed separately. So that means if you're using the color output, you're really calculating 3 noise textures. So it would be the same as doing something like this, and then using a combined RGB with all the factors. So that means that the color, really, you should only use it if you need it, because it calculates 3 noise textures. And that might make it a lot slower. We can also apply this idea of fractal noise to other kinds of noise texture. So for example, this is with the Perlin noise instead of the simplex noise, which uses a triangular grid. Perlin noise is a rectangular grid, which is, like I explained previously, just adding different copies of this noise texture together. Now let's say we use our value noise. The results are also not that bad. And if I decrease the scale to something like 5, I think it looks just as good as regular fractal noise using Perlin noise or simplex noise. It's just that when you start to increase the scale, it starts to look bad. And the one that really doesn't work is using this white noise texture. It just looks terrible, so you shouldn't use it.